Today, on HSC Life Sciences, I'd like to take a small detour and talk about altruism, and specifically how in ethology it's sort of reduced to the ideas of kin selection, reciprocal altruism, and Hamilton's rule. Don't worry, we'll definitely go over all of these. Now, to begin, what is altruism? Now, colloquially, in the sense that you might use it in English, altruism is just sort of a nice deed, just being willing to self-sacrifice, and it carries a similar meaning in biology, wherein it's defined as when an organism's behavior benefits other organisms at a cost to itself. For example, meerkats can give warning signals when predators approach, which endangers themselves and makes them more likely to be caught by these said predators, but also increases other meerkats' chance of survival. Now, this might seem a bit counterintuitive. After all, why would meerkats develop such a behavior that endangers themselves? It just seems against the rules of fitness that Charles Darwin put in his The Origin of Species. However, after some toiling in the 19th and 20th centuries, biologists and ethologists have been able to come up with a general rule for altruism. And to do that, let's talk about the idea of reciprocal altruism. We've already acknowledged that if evolutionarily, it makes very little sense to self-sacrifice, until you consider that the evolutionary objective of life is, in itself, to pass on your genes. And so altruism can actually be a good thing, as long as the altruist receives a reciprocal benefit that is greater than its initial cost. So if this behavior encourages others in a group to, on average, also contribute, um, and, save each other from risks that are greater than the initial costs. That are greater than, yeah, to save them from risks, and in doing so, impart a greater benefit than the cost to themselves, to the group. And so, obviously, you might be wondering how we can quantify this. And to do that, we're going to have to think about who benefits the most from altruism. In talking about altruism, it's obvious that the family members benefit the most. And so, we come to Hamilton's rule. RB is greater than C, or in some forms, RB minus C is greater than 0. All this means is that you take the proportion of shared genes, that's the part I'll go into later, you multiply that by the benefit to the recipient, so how many more offspring is produced. And then you have to see if that's greater than the cost to the altruist. So essentially, the cost is the risk multiplied by the amounts of offspring they would have produced. So it's basically a counterbalance to the benefit to recipient. And what this means is that um, it depends on who like you're saving. Um, yeah, it depends on who you're saving for the altruistic act to be worth it. So let's saving your brother would be different from saving your grandmother. Because they have different proportions of shared genes, even if everything else is the same. An important thing to keep in mind for Hamilton's rule is that it assumes that every organism, every member, will from then on produce the same number of offspring. Obviously, this isn't true in real life, but in a Hamiltonian sense, we're allowed to assume this in order to calculate um, an intrinsic sort of to see to do a qualitative weighing of an altruistic act and to see if it's worth it. Now, we wanted to talk about relatedness first. What does that mean? Well, the way you figure out the value is by taking the coefficient of relatedness. In other words, the consanguinity, or how much genetic material and information you would share. For example, you would share half your genetic information with your brother. That makes the coefficient of relatedness zero point 0.2, half. Similarly, you share half your genetic information with your mother and father. Again, that would make the coefficient of relatedness zero point 0.5, or 1 half. This gets a bit trickier when we're talking about other, more distant relatives. Like your grandmother and grandfather, that's easy enough. That would be 0.25 because they're the mother of your mother. And so thus approximately one-fourth of the genetic information gets carried over. Another common one to look out for is cousins. and that would be 0.125. And the logic behind that is because, well, to think about that, we have to think about how much you share with your uncle and your aunt. And they're the brothers and sisters of your mothers or fathers. So again, they would be 0.25 because they share zero point 0.5 of their DNA with your mother or father, who in turn shares zero point 0.5 with you. So that's zero point 0.5 times zero point 0.5, and that gives you 0.25. And so your cousins, which would be their direct offspring, would share zero point 0.5 of their DNA with their parents. And so that will just lead to 0.125 or 1/8 of your DNA being the same as their DNA. So I hope you understand how coefficient of relatedness works because we're going to need it to solve some Hamiltonian problems. So let's take a look at this first problem. According to Hamilton's law, given that the average number of offspring is 2, which will come into importance, a young man is close to drowning in the heavy surf, and his sister risks her life to swim out and pull her sibling to safety. What cost does his sister incur if she had a 25% chance of drowning in attempting the rescue? Well, let's look at our good friends, the Hamilton's rule. RB is greater than C. Now, let's break this down individually. What's R? Well, that's easy. A brother and sister have a coefficient of relatedness of zero point 0.5. We discussed this earlier. Um, and so that means that R is zero point 0.5. Simple enough. B, we have to look at the benefit. If the young man had drowned, his reproductive output would have been 0. But because we had the information that um, every person is guaranteed to father 2 children, he can father 2 children. So the benefit to the man is thus 2 offspring. As simple as that. So the left side of our inequality is going to be 1. Now, how do we calculate C? I mentioned before that it's the risk times the number of offspring. So in other words, it's pretty similar to the left-hand side, except instead of coefficient of relatedness, we're using risk. And pretty much that's what this equation boils down to. It's comparing the coefficient of relatedness and the risk. So the sister would also have been expected to birth 2 offspring, to mother 2 offspring, and we're told that she has an 0.25 chance of drowning. So the risk is 0.25 times 2, which rounds out to be zero point 0.5. So we know the cost is zero point 0.5. In other words, on average, hypothetically, she's going to lose zero point 0.5 of her offspring every time she attempts this act. And so we end up with the inequality 1 is greater than zero point 0.5. In other words, Hamilton's rule tells us that this altruistic act is worth it. In other words, it is not necessarily altruistic because in our definition of the word, it's not used to define things that are done for benefits. In this case, we can see that truly the sister does stand to benefit from this action. But the biological definition of altruism is different from how we use it today, so I will ignore that and move on to our second problem. Imagine that your grandmother, uncle, and first cousin are all in a boat that is sinking. Without your help, they have a 25% chance of survival. With your help, they have a 75% chance. By Hamilton's rule, what is the maximum likelihood of drowning you would risk to save your relatives if you wanted to maximize your chance of passing on your genes? As we said before, that's an assumption that Hamilton's rule problems make. Assume that you, your grandmother, uncle, and first cousin are all expected to have the same number of additional offspring if you or they survive. I encourage you to stop here, to pause here, and try to figure out the answer to this problem, because it's a bit more of a complex problem, as you might have realized, than the previous one. But given the information that I've gone through today, I think you should be able to get it with a bit of thought. Um, yeah. Okay, so if you haven't paused by now, let's look at the answer, and let's see how I got there. The coefficient of relatedness of you and your grandparents are 0.25. We've gone over that already. With you and your uncle, that will also be 0.25, as we've gone over that already. And first cousin would be 0.125, because recall that if you assume that this cousin is going to be, um, birthed by one of your uncles or aunts, which, is guaranteed to be true, they're going to share half their genetic information. So that's 0.25 divided by 2, which is 0.125. So now what? Well, this operation assumes that um, this rescue act is either going to be successful or it is going to not be successful. So all you really have to do is add up the coefficient of relatedness of everyone to see the net benefit, that yeah, the net coefficient of relatedness, or the net benefit in other words. Now, what's different from this problem and the other problem is that this problem asks you to find the greatest possible risk. In other words, it's asking us to again compare risk and benefit, but it's not asking us to, well, let's take a look at the other problem. It's not asking us to take a look at the cost. In the previous question, the cost we saw was zero point 0.5, right? Because the sister would have been expected to birth two offspring, and she has an 0.25 chance of drowning. So that would have been zero point 0.5. In this problem, we are looking for the maximum likelihood of drowning. In other words, we're looking for the risk, not the cost. And if you recall, the cost is created out of the risk multiplied by the number of offspring. Now, the important thing about this problem is that it never tells you the number of offspring you need. However, it because we have the assumption, as you see in the last sentence, that everyone is expected to have the same number of additional offspring, we can just entirely ignore that variable, right? Like we can, as you see over here, it's represented by x, and we can just divide x from both sides, because they're not relevant. They're just modifiers that are multiplied by our percentages. So, where am I going with this? Where I'm going with this is that pretty much we have r. And as we know, B is the risk. Uh, yeah, B is going to be the net gain. In other words, we go from a 75%, a 25% chance of survival without your help to a 75% chance with your help. In other words, that's a net benefit of zero point 0.5, or other words, 50%. Now, it doesn't matter that we don't know how many offspring that they're going to produce because, well, it's irrelevant. We can just divide x from both sides. So, in other words, our equation comes out to be 0.625 uh, times zero point 0.5. And in other words, this ends up to really show us the maximum risk that we can incur. And this just so happens to be 0.3125, or in other words, 31.25%. Now, that really wasn't that bad, even though we had so many variables and we weren't given some information. We still managed to use Hamilton's rule to its fullest potential and realize and sort of weigh the risk of altruism. It's not something that you think about a ton, but this equation is pretty much intuitive. Um, I think that if you have a solid understanding of it, you can pretty much solve every problem thrown at you as long as you understand and have enough information to solve for the variables present in Hamilton's rule. So, with that, thank you for listening. I hope today's discussion about altruism and Hamilton's rule was a nice little tangent into life science as we dive next week into whatever topic we may. Thank you for listening. I've been Jason Shim, and I hope your evening is doing well.